Hello and welcome to the lesson notes for Chapter 7, Lesson 3, Triangle Similarity, AA, SS, and SAS. We're going to prove certain triangles are similar by using AA, which stands for angle, angle, SSS, which stands for side, 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 and SAS, which stands for side, angle, side. We will also use this triangle similarity to solve problems. There are several ways to prove that certain triangles are similar. We've talked about triangle congruence before, and triangle similarity works very much the same way. The following postulate, as well as side, 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 and side angle side similarity theorems, will be used in proofs just as SSS, SAS, ASA, HL, and AAS were used to prove triangle congruence. So our first postulate today is 731, angle-angle similarity. And here's what it states. If two angles of one triangle are congruent to two angles of another triangle, the triangles have to be similar. Not congruent, similar. Same shape, but different sizes. So in example 1, we're going to explain why these two triangles are in fact similar, and then we will write that similarity statement. So we have triangle ABC and triangle DEC, and we want to prove that they're similar triangles. We do know angle A is a right angle and angle D is a right angle. So here's what we can say. Since AC is parallel to DC, in fact, they're the same lines, angle BCA is congruent to angle ECD by the vertical angles theorem. Also, we know angle A and angle D are congruent by the right angle congruence theorem because all right angles are congruent. So I've shown two pairs of angles congruent. That means triangles are similar by angle-angle similarity. And so this is the similarity statement we will write. Triangle ABC is similar to triangle DEC by angle-angle similarity. We want to put that similar symbol after AA. To check whether or not you've gotten the order correct, angle A is the right angle and angle D is the right angle, so they should be first in line. Angle B is not one of the vertical angles, so the angle that comes after D should be E, the other one that's not one of the vertical angles. And then lastly, we both finish at C. Next, we have theorem 732, or side, side, side similarity. We do have to put that similarity symbol or the word similarity after SSS because it is different from side, side, side congruence. Side, side, side similarity says this. If the three sides of the triangle are proportional to three corresponding sides of another triangle, then the triangles are similar. We also have side angle side similarity. It says if two sides of one triangle are proportional to two corresponding sides of another triangle, and the included angles are congruent, then the triangles are similar. So in example 2a, we want to verify that these two triangles are in fact similar. And the order is important. The order gives you the corresponding sides and corresponding angles. Now, triangle PQR, we are given the side measurements and no angle measurements. Same on triangle STU, sides only, no angles. So we would be trying to use side, side, side similarity. So here's what we must show, that the relationship or ratio of each corresponding side to its other corresponding side is the same for both triangles. So we can compare PQ to ST. Since these are both isosceles triangles, you could also compare PQ to UT, but that is not what the order tells us. PQ and ST come in the same order, so that's what we would compare. That would be 3 to 4.5. When you simplify this ratio, we get 2/3, 2 to 3. We want to try another set of corresponding sides, so we're going to try QR and TU, also having the ratio 3 over 4.5, which simplifies to 2/3. We don't want to leave a decimal within our ratio. And lastly, we want to try PR and SU. 2 to 3 is the same ratio as the others. Therefore, triangle PQR is similar to triangle STU by side, side, side similarity. And this is what we would write, this last sentence. Let's take a look at example 2b. we are given triangle DEF and triangle HJK. From the label here, D corresponds to H, E corresponds to J, F corresponds to K. So we want to check for similarity with either side, 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 or side, angle, side. Looking at these two, we are given two sides of one triangle and their corresponding sides of the other. And we're given the included angle of each. So we're probably using side, angle, side. So here's what we can say. Angle D is congruent to angle H by the definition of congruent angles. They have the same measure. Now we want to check the proportionality of corresponding sides. DE corresponds to HJ. That ratio would be 2 to 1, which is just 2. And I want to check the ratio of the other sides, DF and KH, the other two given sides. DF to HK is 5.8 over 2.9. When you reduce that, that is the same ratio, 2. Therefore, we can say that triangle DEF is similar to triangle HJK by side, angle, side similarity. SAS, and then the similarity symbol. Again, make sure you write this last sentence. That is the final part of this problem. Let's take a look at example 3. We need to give an explanation as to why triangle ABE is similar to triangle ACD. And once we've done that, we can find DC, or CD. So let's look at what we were given in each triangle. Triangle ABE is a right triangle. We have a right angle at B. And triangle ACD is also a right triangle. Now we're also given side lengths of triangle ABE, and we could calculate the total side length AC, but we don't know side length DC. So I'm not going to be able to use this side to prove that the triangles are similar. But what I can notice is that I have two right angles here, which would have to be congruent, and both triangles share angle A by the reflexive property it's congruent to itself. Therefore, since angle A is congruent to itself by the reflexive property, and angle B is congruent to angle C since they're both right angles, the triangles are similar by angle-angle similarity. Now that I've shown that, I can set up a proportion to find the length of CD. To find CD, we know the legs of triangle ABE. One leg is 9, one leg is 5. I need to find the length of AC. Well, we're given 9 is AB and BC is 3. If I add those together, using the segment addition postulate, I can get this ratio. Now, most of us are going to jump straight to writing in these numbers. By substituting x for DC, or CD, it corresponds to BE, 5, so that ratio, x to 5, would be the same as the ratio of the full side AC, which is the sum of these two parts, over AB. So x over 5 equals 3 plus 9 over 9. Well, you'll notice 3 plus 9 is 12, so x over 5 equals 12 over 9. In order to solve for x, we use the cross products property. Why don't you take a few moments, solve this proportion, and when you have a value of x, that will be the length of CD. When you're ready, you can continue by pushing play if you've paused the video, and check your result. Okay, we should get the following result. In solving this proportion, we should get x equals 6 2/3. Make sure you write it as 2/3, not 0.3. If you wrote it as 6.3 repeating, that's okay, but we always prefer to write the most exact possible answer unless we're told to round. And you're not told to round, so we want to write the answer as a fraction, 6 2/3. If you simplified or reduced the fraction, left it improper, that's okay as well. But most of us probably got 6 2/3. All right, now for example 4, we do have a proof here. And it's been a little while since we've done a formal two-column proof, but we're going to try and piece this together and see if we can meet the criteria to prove that triangle UVT, which is the one here on the right, is similar to triangle RST. Now, UVT and RST, the order of those letters tells you which angles and sides should correspond. U corresponds to R, V corresponds to S, and both angles at T are corresponding angles. We need to start with what we are given. Now, you'll notice the given information is that 3 times UT equals 5 times RT, and 3 times VT equals 5 times ST. what these might look like to you, at least I hope they will, these should look like cross products. That means I can write a proportion out of this cross product and a proportion out of this cross product to show that the ratios are equal, or that the side lengths are proportional. I've got UT and RT. UT and RT are corresponding sides, and VT and ST, those are corresponding sides. So there's a pair of corresponding sides that I should be able to show are proportional. And you'll notice that we have intersecting lines here, so these vertical angles are congruent. So I'm most likely going to use side angle side similarity to show that these are similar triangles. Let's take a look at what the proof should look like. So you'll notice here we separate our statements and reasons into columns. We want to start with our given. And notice I'm going to start with one given at a time here. We don't always have to do that. You could do this a little bit differently if you're doing it on your own, but I'm going to separate the givens. Since 3 times UT equals 5 times RT, I'm going to rewrite that as a ratio of UT over RT. UT divided by RT would be 5 divided by 3. By dividing both sides by 3 and RT, we get this. Or that could be the division property of equality. I can do the same thing with the other given. 3VT equals 5ST. You notice my reason might be stated a little bit differently by getting VT over ST is also 5 over 3. We divide both sides by 3ST. So what I've shown here is that the ratio UT over RT is equal to the ratio VT over ST. And remember, I have vertical angles, so angle RTS is congruent to angle VTU by the vertical angles theorem. Step 2 and 4 shows that corresponding sides are proportional. Step 5 shows that the included angles of both are congruent, so the triangles are similar by side angle side similarity, steps 2, 4, and 5. All right, in example 5, we have this photo here, shows a gable roof in which AC is parallel to FG, and we're told that triangle ABC is similar to triangle FBG. That would mean their corresponding angles are congruent and their corresponding sides are proportional. We want to find BC to the nearest tenth of a foot. So here's what we need to do in order to set that up. Now, we can assume that triangles ABC and triangles FBG are, in fact, isosceles triangles because they are parts of a roof line like this. Okay, so we're going to make that assumption. And in order to do the rest of the problem, that will be very important, because what that tells us is that AF is 17 and also GC is 17 feet. So what we need to find BC is to find BG, which is the same as BF. So here's how we're going to set that up. Remember that in similar triangles, side lengths are proportional. So we can say that x over 6.5 equals the same corresponding side of triangle ABC, which would be x plus 17 over 24. Remember, in finding BA, we will find BC. Both of those would be equal to x plus 17. So I need to find out what x plus 17 is. So in order to do that, I'm going to find out what x is. So we're going to cross multiply here and get that 24x equals 6.5 times x plus 17. And when we do that, when we distribute the 6.5 to both of these, we get that 24x equals 6.5x plus 110.5. I'm going to let you continue to work this out. You'll need to pause the video. We're running out of time. But once you're ready, click play to check what the answer should be. All right, you should get that x is 6.3 approximately. So when we plug that in to find BC, we should get that BC is about 23.3 feet.